So you must have studied about breakdown while studying the VI characteristics of diode, haven't you? Breakdown, reverse breakdown.
Yes, sir.
You must have studied. Yeah, yeah. Somebody replied yes, they have studied. Okay. So how many kinds of breakdown are there in diodes? In diodes, we have something called breakdown. More specifically, we call it reverse breakdown. So how many kinds of reverse breakdown you have studied? In reference to diodes, what are the types of reverse breakdown? Yes,
Two.
two. What are those?
Two.
Zener
Zener
and
and avalanche.
avalanche. Avalanche.
So one is zener breakdown, another is avalanche breakdown. So out of these two, which one takes place at a higher reverse breakdown voltage? Which one of these breakdowns occurs at a higher reverse bias voltage?
Zener.
You have to justify. Zener is not correct. Actually, it is avalanche breakdown. The avalanche breakdown takes place at a higher reverse breakdown voltage. Okay. So, although both are breakdown, both the phenomena supports a process called breakdown, which occurs in the reverse region of the VI characteristics of diode. है ना? The region where this VI characteristics is observed, it is called as zener region. Okay, this is your VI characteristics. If you can relate, this is voltage axis, this is current axis. Somebody joined. Let me allow him. Okay. So if you see the VI characteristics of any diode, in the forward bias, the characteristics is somewhat like this, and in the reverse region, it is somewhat like this, or you can say more specifically, if to be more accurate, let me do it in some more detail. In the reverse region, the VI characteristics will be somewhat like this. Okay, so if you increase the reverse bias across the diode, there is a very small amount of current, which we call it as reverse saturation current, and that stays for a while we are increasing the reverse bias voltage magnitude. So we are increasing the reverse bias voltage, the current in the current through the diode. Okay, how do we apply a reverse breakdown, reverse bias voltage in this manner? In this manner, in this circuit, the diode has been reverse biased. This is minus, this is plus. That means higher potential has been provided to the N side of the PN junction diode. The lower potential, that means N type is at a higher potential with as compared to the P side. So that is reverse bias. So in this connection, in this circuitry, when I am saying that we are applying a reverse bias and we are increasing the reverse bias, we are basically we have a variable voltage source. We are increasing this so that the reverse bias voltage across the diode is increasing. That means this point is getting more and more positive, more and more higher with reference to this. This is at higher potential than this. While I am increasing this is getting more and more higher as compared to this. So that is what I mean by increasing the reverse bias. So while I am increasing the reverse bias, I am moving in the x direction towards left. So while I am doing this, the current through the diode is not increasing much. Although I am increasing the reverse bias, the current is not increasing much. Suppose for this reverse bias voltage, the current was this much. The current was this much, which is IS, reverse saturation current, IS. When I moved by increasing the reverse bias voltage to this point, the current has not increased much. It has stayed at IS current only. And keep note of it that the direction of IS is in this direction. That is opposite to the direction of diode. Diode direction is this, but the IS current direction is this. This is a reverse current. That's why it is a reverse current. And this IS is in microampere range. So what is breakdown voltage? Breakdown voltage is that voltage beyond which if you will increase the reverse bias, you are increasing the reverse bias. So a point will come when this is at a higher potential than this by Vz, and then the reverse current is no more IS. It is no more IS. It increases beyond IS, beyond the reverse voltage. When it exceeds Vz, this voltage, when you are increasing so much that this is at a higher potential than this by Vz, the reverse current is no more at the saturated current value, that is IS. It increases beyond it, and then we say that we have got the breakdown occurred, and this region is called as breakdown region, or more popularly it is called as the zener region. It is more popularly called as zener region. So it is that region of the VI characteristics of the diode in which the breakdown phenomena has taken place. So this breakdown can occur either due to zener breakdown or avalanche breakdown. So both can simultaneously support this breakdown phenomena. But the avalanche breakdown process is more prevalent or more dominating at a higher reverse bias voltage, whereas this zener breakdown can take place at a lower reverse bias voltage also. Okay. So now talking about these diodes, which we are calling them zener diodes. So what is the specialty of these zener diodes? So before talking about these special diodes, these very special diodes which we are calling it zener diodes, let us talk about what is the limitation of a normal diode. So before learning about a special thing, we should first realize what is the normal, what is the thing that is taken under normalcy. Okay, so for normal diode, okay, for a normal diode, this current is too much, this much of current. If you let the diode, suppose this is a normal diode, and you have biased it so that it has been this voltage across it is Vz. In that case, if there is this resistance is very less value resistance, okay, so the current will be too much in the reverse direction. So once this diode has got across it a voltage which is Vz, enormous amount of reverse current can occur through it. Okay, once this Vz across it is Vz, huh, so the voltage across this diode is once Vz, the current through it can be enormous because it has already reached the zener region. So how much current will flow through this diode in that situation will be controlled completely by this current limiting resistance. And if this current limiting resistance is so very less, let's say if it is 0, suppose this resistance is 0, then a very high amount of current will flow through this diode in the reverse direction. And remember, this is what I am talking about is normal diode. So in that case, that high current will damage this diode itself. Okay, very high current will damage this diode in such a way that this diode will lose its very VI characteristics. Even if you once a very high amount of current flows through it for some time, after that if you try to use this diode, it will not show the same VI characteristics for which this diode was designed for, manufactured for. Okay, so that is the problem. So we say that the diode has been damaged. So once the diode loses its VI characteristics, we say the diode is no more usable. It has been damaged. So if this high amount of current flows through a normal diode, the very high amount of reverse current flows through this normal diode, we lose that diode. Okay, the diode is no more usable in future. So this is the limitation of a normal diode. We cannot use the normal diode in the zener region for long. A very small amount of this region operation will damage this normal diode. But and here we can distinguish a zener diode, a special kind of diode which is called zener diode, which can withstand this situation, this zener diode can withstand this situation which otherwise the normal diode couldn't. Are you getting? Hello? Hello students, are you getting?
Yes, sir.
Okay.
Yes, sir.
Okay. So a normal diode in it's okay. Usually a physical diode, अगर तुम lab में देखोगे, it looks somewhat like this. Okay. Okay. There is a strip. But in while we use the diode in circuits, let me show you for reference how a physical diode looks like. So you see here in this figure, this is the physical diode. This is the diode, how it looks when you hold it in your palm. On your palm, when you hold a diode, you have a physical diode, it looks somewhat like this. But this is a symbol for the diode. This is the symbol for the diode. Whenever you refer to a circuit in which the diode exists, you do not use this kind of representation. You use this kind of representation in a circuit for representation. So this is the circuit symbol of diode. So this is the circuit symbol of diode. So this is P side, this is N side, or otherwise you can say this is anode side and this is cathode side. So this is for normal diode. Your zener diode looks somewhat like this. This is the symbol for zener diode. Okay, this is the symbol for zener diode. Okay, so this is P side, this is N side, this is anode, this is cathode. Okay, So what is the specialty? If it is a special diode, so what is the specialty of this diode? So uh, this zener diode has got higher doping. Okay, so this zener diode, how it is manufactured and how it is different than the way it is manufactured. The normal diodes are manufactured. Whatever doping concentration prevails for a normal diode, the doping concentration in the P side and the N side is much higher in the case of zener diodes. Okay, the doping concentration in the zener diodes is very high. So high doping is a very characteristic feature. High doping is a very characteristic thing which prevails for this zener diode. Okay, and this supports and this results to bring down the zener breakdown voltage to lesser values. Usually your normal diode, usually your normal diode will have a high zener breakdown voltage, but uh, typically typically around 15 20 volts, around that 10 volts, like that for a normal diode. But for a special diode, for this zener diode, this zener breakdown voltage for this zener breakdown voltage can be as low as 2 volt. This can this can be so, the zener breakdown voltage can be as low as 2 volt, just because of this high doping concentration which has been taken care of during the manufacturing of this zener diode. Okay, and in the breakdown phenomena, we already know that there are two types of breakdown: the zener breakdown and the avalanche breakdown. So during the breakdown phenomena, in the case of zener diodes, the zener breakdown is more dominating. Okay, the zener breakdown dominates the avalanche breakdown during the breakdown that occurs in the zener region. Okay, so what in the breakdown region, which breakdown dominates? The zener breakdown dominates. So this is the difference between uh, this normal diode and a zener diode. And and you just keep in mind that this zener diode can be operated in this zener region for not thinking much about how much time I can do it without damaging the diode. Okay, these zener diodes are designed to be operated in this zener breakdown region only. Okay, this normal diodes cannot be operated for long, not even for a minute. You cannot do it for normal diodes, but the zener diodes can be operated for uh, you can say it has a lifetime, it can use for its lifetime in being operated in this zener region. Okay, so basically what I mean to say is this zener breakdown is meant, the zener diode is designed, or it is meant to be used in this zener region only. So it will not be getting damaged while being operated in this zener breakdown region, while a normal diode gets damaged. That means even if you operate a zener diode in the breakdown region, it doesn't lose its VI characteristics. It doesn't lose its VI characteristics. It doesn't lose its VI characteristics. The VI characteristics is retained by this zener diode for its entire life. So a zener breakdown, even if operated in the zener region for as long as you wish to, the diode keeps retaining the VI characteristics or the typical VI characteristics of the diode. Okay, so that is the benefit of using this special diode, which we are referring to as zener diode. Okay, so now this was something you must have studied in the basic electronics theory. Just for recall sake, just for revision, I just got into it. Now let us come to the application part, where we are trying to apply this zener diode. That application is as a voltage regulator. The application is using this zener diode as a voltage regulator. So first of all, let us try to understand what a voltage regulator is expected to do for us. Voltage regulator is some system which is going to solve some problem for us. So what is that problem? So for with it comes with a solution for which problem of us we should first realize. Okay. Okay, anybody? What a voltage regulator is expected to do? Somebody? Okay, Himanshu Sekhar says that maintains a constant voltage across any device. Okay, let us Google, huh? Let us Google what a voltage regulator is. So the Google gives me a page from Wikipedia which says a voltage regulator is a system designed to automatically maintain a constant voltage level. A voltage regulator may use a simple feed-forward design or may include negative feedback. It may use an electromechanical mechanism or electronic components. So anyway, so you just give some emphasis on this first line. A voltage regulator is a system designed to automatically maintain a constant voltage level across what? Across our appliance. Across our appliance is going to act like a load in this circuit. Okay, so we want to safeguard our appliance against what? Voltage fluctuations. Okay, so basically the voltage regulator will help us to maintain a constant voltage across the our appliance, whatever appliance we are going to use. If we want to maintain a constant voltage across it, we need to use a voltage regulator. So let us see. So where does this voltage regulator will come? Kahan pe? Where will we find a voltage regulator? So let us recall our rectifier operation. So you had a sinusoidal signal like this. Okay, you rectified it. You used some rectifier circuit and you got a waveform somewhat like this. Let's say it was a full wave rectifier. So the waveform which came out of the full wave rectifier was somewhat like this. Okay, it was somewhat like this. Then again, if you used a rectifier with capacitor filter, we have not done the experiment with rectifier experiment with capacitor filter, but let's say we have used a capacitor filter rectifier using a capacitor filter, a waveform would have been somewhat more suitable, more well rectified signal. In that case also, the signal would have been like this. So this is having lesser ripples as compared to this without capacitor output. This is with capacitor and this is without capacitor. So anyway, the voltage is not constant. If you see, whether maybe in this case or you may see in this case, the voltage is not constant. It is still changing. Although the change in voltage is lesser in the case where we are using a capacitor filter, and it is more in the case where we are not using a capacitor filter. In what is common in between them is uh, some amount of voltage fluctuation is there, and we know that the ideal DC voltage which we expect from a DC source is somewhat like this. Let's say I want 2 volt DC. Okay, so over time the voltage should not change. So that is the most expected, most desirable form of DC voltage, DC source we want to have. A DC source should give us a signal, a voltage signal, which is somewhat like this. Then we say that is a desirable DC source. So what can you do to get a constant voltage from this? The rectifier gave you this. So how to get somewhat a signal which is more closer to this? So there you need to use this voltage regulator. Okay, there this voltage regulator comes for rescue. So what you can do? So what a typical voltage regulator does? Okay, let me. So let's say this signal. Okay, if I put it through a voltage regulator, what will happen? Okay, voltage regulator will regulate the voltage such that the output of the voltage regulator doesn't go beyond a certain reference voltage. Okay, suppose this is let's say somewhere this is some value, this is some value, this signal touches a peak value of let's say 2.5 volt. Okay, and this is somewhere which is 2 volt. So suppose I have designed a voltage regulator which restricts the output not to go beyond 2 volt. So what will happen in response to, okay, मैं नीचे ऊपर नीचे बनाता हूँ तो better होगा. Okay. This is let's say V input and this is V output, which is expected at the output of the voltage regulator. So the input signal is somewhat like this. Okay. So I am doing the corresponding output just below it. So this is Vi, this is Vo. So I'm going to, this voltage regulator is going to limit the output voltage up to a maximum of 2 volt, up to a maximum of 2 volt. So when Vi is, so what, how the V output will be managed? Whenever the Vi is more than 2 volt, Vi is more than 2 volt, V output will be 2 volt only. Okay. So that, okay, like this. For any Vi, so how the voltage regulator is working? Whenever Vi is greater than 2 volt, V output will be equals to 2 volt. And what else? If Vi is less than 2 volt, then V out will be equals to Vi. Okay, so this is how this voltage regulator is going to operate. So whenever Vi is greater than 2 volt, this is 2 volt, huh? This is 2.5. So whenever Vi is more than 2 volt, you see the rule here, V output will be 2 volt. Whenever Vi is less than 2 volt, Vo is equals to Vi. But in our case, Vi is always more than 2 volts. So that's why the V out will be a constant 2 volt at the output. In case, in case this signal would have come, if would have been coming down, अगर ऐसा होता, in that case, the voltage regulator would have produced a signal which dips down at these points, because what's the reason? Because जब भी Vi is less than 2 volt, Vo is equals to Vi only. Okay, so in that case there would have been a small dip here. Are you getting? A small dip here, a small dip here. So this would have been the regulated output voltage if this kind of input would have been given to the voltage regulator input. So anyway, you are getting a more of a constant output voltage at the output of a voltage regulator, and this is more suitable for our appliance which is designed to operate at 2 volt DC voltage. Suppose your appliance is designed to work at 2 volt DC voltage, then rather than giving this kind of signal, this signal may have been whatever, suppose ये V इसका VDC 2 volt भी रहा हो या 2.2 volt भी रहा होगा, still then if you have some kind of signal which is more of constant, it remains constant for a more interval of time, then it is a better form of DC. It is having lesser ripples. Lesser ripples hona is a better form of DC. So if you can provide a DC voltage of this sort, okay, it is more suitable for your appliance which works on DC. This will enhance the lifetime of your appliance. Okay, are you getting? Hello. Okay, so how are we going to implement this voltage regulator circuit which regulates the voltage such that it becomes more kind of it gives a constant output voltage, है ना? It still more decreases the ripples, है ना? ये जो थोड़ा बहुत ripples रह भी गया था even after applying capacitor filter, उसको भी हम लोग कैसे हटा सकते हैं by using a voltage regulator. Okay, so whenever you have a let's say your mobile charger. Okay, you have a mobile charger. So at the mobile charger, let's say it charges at 6 volt DC. Your mobile charger gives a 6 volt DC to charge your mobile device. Okay, so how do you get this 6 volt DC? You need to have a rectifier stage first. Okay, you need to have a rectifier stage first. The rectifier is put to a capacitor filter. The rectified output is given to a capacitor filter so that ripples are somewhat reduced by using this capacitor filter. So capacitor filter reduces the ripples, but it is still not ripple free. If you want a constant DC voltage, okay, so the ripples should be such that the signal is well above the required 6 volt. Let's say we have a 6 volt requirement, 6 volt DC requirement. So the signal should be such that even in the presence of ripples, it should be well above the 6 volt range. Okay, 6 volt range के ऊपर होना चाहिए ripples. and then if we'll apply this signal to a voltage regulator which limits the voltage to a maximum of 6 volt by this rule, है ना, यहाँ बस 2 की जगह 6 कर दो. Okay, then you will get a voltage suitable to charge your mobile device if the mobile device has been designed to designed such that its battery charges for with a DC signal of 6 volt. If it is designed to get charged, its battery is such managed that it gets charged at a DC voltage of 6 volt. You need to have this arrangement: a rectifier stage, a capacitor filter stage, and then a voltage regulator stage. Then only you get a suitable signal which can charge up your mobile device, which is designed to charge with a 6 volt input, 6 volt DC input. So this is the importance of voltage regulator. Okay, so इसीलिए हम लोग पहले rectifier पढ़े, and then we are studying the voltage regulator. The sequence, if you'll interchange, it kind of distorts the sequence how it is arranged in a typical circuitry in a let's say your AC to DC power adapter. Okay, so that is the sequence we apply, and that is the sequence we need to study. Okay, so how are we going to design a voltage regulator using a zener diode? So a typical and a very simple voltage regulator can be designed with the use of zener diode. The very characteristics of the zener diode, which we have already discussed, will help us to realize and understand a voltage regulator which can be implemented by using this zener diode. So the circuit will look somewhat like this. I'm drawing. So this is a zener diode. So the symbol is like this. A Z kind of symbol appears in the symbol itself. Okay. This is a current limiting resistance, and this is your load resistance, which will represent your appliance, which needs to be protected. Okay, so this is your resistance RL. So this is your zener diode, and your this VI is here. What is this VI? This VI is coming from a rectifier. Okay, this VI signal is coming from a rectifier output. So this is important. Okay, you should realize what is this VI, where to get this VI. This VI is not a DC signal. It is a kind of rectified output only, with or without capacitor. It depends upon you. Of course, the with capacitor will be a preferable one, but anyway, this VI is the output of some rectifier stage. Okay, and here you will get a DC signal which is almost constant, which is more preferable, so that you can use it for your DC appliance. So how this is going to work with the things I have said here, मैं voltage regulator के बारे में जो भी यहाँ बताया हूँ, how this gets reflected by this circuit? Oh, okay, that is the question. So let us realize. You know voltage divider rule? Do you know what is voltage divider rule? Yes or no?
Yes, sir.
Yes, sir.
Okay. So let's let's say for a while I erase this diode. Okay, I have erased the diode. Now, will somebody tell me what is VL in this case? Use the voltage
The
divider.
VI
VI into RL by R plus RL.
Yes, I couldn't hear. Yes, what will be this VL in this circuit? Somebody just reply.
VI R by R1 plus
I'm not getting your
RL.
voice.
VI into R by R plus RL.
Again.
VI plus no VI into RL by R plus RL.
Yes, VI into RL by R plus RL. Okay. So this is the voltage that appears across this. If suppose this is the VI applied at the input of this circuit, then this across RL, the voltage that appears is VI times RL by R plus RL. Okay. So here I have assumed that there is no diode placed here. So suppose let's say I place this diode over here. Okay. So in that case, this VL will appear across this diode also because these two components are in parallel. So whatever VL you have calculated using this VI, R and RL, that very voltage will appear across this diode also. So when this VL, when VL is greater than the zener breakdown voltage, this is a zener diode, so this must have some zener breakdown voltage Vz, and this zener diode must have come with some zener breakdown voltage Vz, which you can always find from the specification sheet. So if this VL is greater than Vz, okay, if VL is greater than Vz, the zener diode will be pushed to the breakdown region. In that case, the zener breakdown will be getting on in the reverse region. You can say, agar if zener diode is pushed to the zener breakdown region, we say that the zener diode has been on in the reverse direction. We can say so. Okay. If we can, if we have the diode such that the operating point is in the zener region, it is same as saying that the zener diode is turned on in the reverse direction. So if VL is greater than Vz, okay, then the zener diode is on and the current can flow in this direction. In this direction, the current can easily flow with least of resistance in the direction opposite to the diode direction, because anyway this is a reverse bias. So what will happen? This is the case when this condition appears. But what if this VL is less than Vz? क्या होगा बताओ? If VL is less than Vz, of course the zener diode will be off. The zener diode will be off. That means operating point is somewhere here. That means a current can exist, but that is only the reverse saturation current, and which is so less in the microampere range that it is almost ignored, which is ignored. So it is as good as there is no current. If a current exists, which is equal to the reverse saturation current, it is as good as no current. It is so less of a current. So we assume that in that case, this zener diode is off. So the zener diode is on when this VL calculated is greater than VZ, and the zener diode is off if this VL calculated is less than VZ. If VL is less than VZ, the zener diode is off. That means no current can flow through it in this direction. There is no current in this direction. So you can, in this very case, the zener diode can be replaced by open circuit. Okay, if VL is less than VZ, then this zener diode can be replaced by open circuit. Okay, if VL is less than VZ, the zener diode can be replaced by open circuit, and in that case, the V output will be simply equals to VL. अगर ये zener diode open circuit से replace किया जा सकता है, there is no current through this zener diode. Okay, V output is simply this equals to this VL calculated for very obvious reasons. Okay, but what if the zener diode is turned on? What if this zener diode is turned on? Turn on कब होगा? This Vi is sufficient enough to make this VL, है ना? Vi is completely influencing the value of VL. Vi बढ़ाओगे तो VL बढ़ेगा. So if VL is high, it can be as high for a particular value of Vi that it is greater than Vz. If this condition happens, VL is greater than Vz, the zener diode gets on in the reverse direction, and there can be a enormous amount of current through this diode in this direction. Okay, and for that situation, V output that is observed across these two terminals. What is the potential difference between this point and this point? V output will no more be equals to VL. It will be no more be equals to VL, but in that case, V output is equals to Vz. Why? Because once the zener diode is pushed into this breakdown region, the voltage across it, the voltage across the zener diode is fixed to the value of Vz. And since these 2 points, okay, the potential difference between these 2 points has to be equals to the potential difference between these 2 points, because these 2 branches are in parallel. So V output for this condition will be equals to Vz. And this is the exact same thing which we expect out of a voltage regulator. Okay, so that means the output is regulated up to a maximum voltage of Vz by this sort of voltage regulator. Are you getting? The output voltage is regulated to a maximum of Vz by this voltage regulator which has been implemented using a zener diode. When VL is less than Vz, V output is simply VL. When VL is greater than Vz, the V output is simply Vz. Okay. So it will, the VO will never be greater than Vz. This voltage regulator will not let the output voltage to go beyond Vz. And this is the manner in which the voltage regulator is going to function. Are you clear? Everybody, are you clear? So whatever I have told you now, this must not be a new thing. Okay, It should work just like a revision, but still you should be very clear while I'm explaining. So are you clear?
Yes, sir.
Okay. So I want some responses in the chat box. Are you following or not? Okay, fine, fine. So let us start implementing. Okay. Or we can discuss something else on this topic. What other things can be related? What more analysis can be done? Okay, let us see. So in a very usual case, this Vi that is coming here, it is variable, isn't it? It is time varying. Variable means it is time varying. I told you this Vi is coming from the output of a rectifier with or without capacitor, preferably with capacitor filter. Okay. So anyway, this Vi is a function of time and it is variable. Okay. And this RL is fixed. This R and RL, this RL and R are fixed. Okay, by the designer himself, this R and RL is fixed for a typical condition. For a typical voltage regulator circuit, this R and RL are fixed. So this is a scenario which will be seen in most of the cases. In some special cases, it may happen this RL is varying. Okay, we'll not consider that case when the RL may be varying. That means the load resistance is varying. Okay, that may be a case in some scenarios, but we will not discuss for the time while. Will be more specific to a scenario in which this Vi is variable. This is more obvious. This being the output of a rectifier, it is most expected to be time varying. Okay, and this will assume that this R and RL are fixed. Okay, this is a current limiting resistance. Okay, you should know the significance of this resistance. Why we have placed this? To limit the amount of current that enters into this circuit. Okay, so this is a current limiting resistance and this is your load resistance, the resistance of your appliance, and this is of course your zener diode. So this is the configuration of a typical uh, voltage regulator using a zener diode. Okay. So here, can you calculate what is the minimum value of Vi? What is the minimum value of Vi that is required to turn this zener diode on in the reverse direction? Can you do it? Can you calculate? Yes, I want you to calculate, or you can find an expression that gives you Vi minimum that is required to turn this zener diode on in the reverse direction. Are you getting or not? Suppose let's say Vi equals to 0. Let's say Vi is equals to 0. In that case, VL is equals to 0 because VL is Vi into RL by R plus RL. So VL is becomes equals to 0. So if this zener diode has got a zener breakdown voltage of Vz, so of course you will check for this condition. Hai. So 0 is greater than Vz. No. So 0 is less than Vz because Vz has to be some finite quantity. Are you getting? So in that case, the zener diode is off. The 0 is less than the Vz. Let's say the Vz is 2 volt. 2 volt means Vd is equals to minus 2 volt. Okay. You should take note of it that we mentioned the Vz, suppose 2 volt, that basically says that Vd is equals to minus 2 volt. So when we say that give some Vz value, that is the magnitude of it. Okay, Vz is always a reverse bias voltage. So you should understand that Vd is a negative of that Vz. So that is the way of understanding the values. Okay. So anyway, if Vi is 0, VL will be equals to 0, and in that case 0 will be less than Vz. 0 is less than Vz and the diode is off. So that V output is equals to VL, and which is of course 0 for this case because VL is 0. So what I want you to calculate to find the expression, that what is the minimum value of Vi which will let this zener diode to turn on in the reverse direction. Yes, calculate. Calculate. I want some answers. Get me the expression. Are you getting the question? Yes or no? Hello. Hello, just respond to me, somebody. Somebody just respond to me. Am I audible or not?
Yes, sir.
Okay. Did you get my question or not?
Yes, sir.
Okay. Try to reply. Okay. Take your time. Okay. I'll give you 2 minutes. You just find the expression to find out Vi minimum that is required to turn the zener diode on. I have given you the analysis over here. କେହି reply କରିପାରିବନି? Somebody should answer, no? Okay, somebody replied. Yeah, he's correct. Rituparna Patasahani. Okay, he is correct. Okay, yes, the derivation is quite simple. You see, Okay. I was asking what is the VI minimum that is required to turn the diode on. Okay. So you know that whenever VL is greater than or equals to VZ, then the diode is going to be turned on. Okay. So VL should be at least equals to VZ. So let us do it. VL equals to VZ. This is the least VL that will let the zener diode to turn on. So VL is equals to VZ. How do we calculate VL? VL is VI times RL by R plus RL. Okay, that has to be equals to VZ. So this gives you VI is equals to VZ into R plus RL by RL, and this is the VI that is least required. So this is VI minimum. Okay, this is what we are solving for. This is the VI minimum. So this is the minimum value of VI that will let it will which will give you VL, which is at least equals to VZ. So this is the amount of VI minimum. If you have some VI, if you'll have some VI which is greater than this VI minimum, of course the VL will be sufficient, okay, more than sufficient to be greater than VZ. Agar for this VI minimum, okay, let me state it once again. For VI minimum, VL, this thing goes to VZ. This RHS goes to VZ. So VL is equals to VZ for VI minimum. So VL equals to VZ means the diode is already on. When you have some VI which is more than VI minimum, then of course the VL is greater than VZ. In that case, VL is greater than VZ, and that has to turn the diode on again. So any VI, for any VI greater than or equals to VI minimum, that this zener diode will be turned on in the reverse direction. Okay. Okay, let us go to the simulation now. Achha, one more thing you should put into this analysis is that if this is the VI minimum, what is VI maximum? What is the VI maximum that you can apply? What is the VI maximum that you can apply to this system? It is not that any input voltage of any maximum value you apply and the output will be regulated DC voltage. No, it is not so. There is a limit of up to what VI maximum this voltage regulator can regulate can do the voltage regulation. Okay, for what maximum value of VI this voltage regulator can do the voltage regulation, the way it has been doing, the way we have discussed here. Okay, so I'm giving you a hint. This VI max will be decided by how much maximum current that can go through this diode in the reverse direction. Okay, that will let you decide what will be VI max for any diode, even for the zener diode, more specifically for the zener diode. The characteristics, if you can recall, is like this. Okay, the characteristic is, okay, let me do a more fair diagram. So the characteristic is like this. Okay. So this is reverse saturation current. This small current in microamperes is the reverse saturation current, IS. This is the knee voltage. Okay. How can represent VT? So as I have already told you that once the diode is turned on, that means the voltage across the diode is already VZ in reverse direction. The diode is on in that case. The current in such a scenario can be enormous. Okay, the current through the diode, when the diode is on in the reverse direction, or you can say that when the diode is already in the zener breakdown region, the current through it can be enormous. And how much current through it prevails in that situation is controlled by some current controlling resistor. So here this is the current controlling resistance. So even in the absence of a current controlled resistance, there is in the specification sheet, you will be provided a maximum current that is supported by this zener diode. Okay, with or without the presence of this current limiting resistance, there is always a maximum amount of current that this diode can support. If you try to exceed that maximum current range, current value, the diode will not be okay. It will be again damaged. Okay, that is a maximum current. This is current axis. This is current axis. This y axis. So there is always some certain current value somewhere in the breakdown region only, that is called as IZ max. IZ max. So this is the maximum current that this diode can withstand. Of course, this being a zener diode, it can withstand reverse current up to a very high limit, but not infinite, not up to an infinite limit. It is up to a certain current value IZM. Okay, इसके नीचे का जो भी current है, that is a safe zone. If you make a circuit which which lets a current to go through the zener diode in the reverse direction that is more than IZM, this zener diode will be getting damaged. It will lose its VI characteristics permanently. It will be no more usable from next on. So this IZM must be taken care of. If you want to use this zener diode for a very long time, you must take care of this IZM. And this IZM will let you calculate what is the maximum value of VI that you can apply. Okay, what is the maximum VI that can be that is okay to give at its input to the voltage regulator system which we have designed using a zener diode. Okay, so we have calculated the expression for VI minimum. It is a task for you. Okay, you just use your pen, paper, and whatever analysis we have made, and the idea I have given you about this IZM, and you can use the simple Kirchhoff's current law and voltage law to get the value of this VI max. Okay, you just find out this VI max for a typical voltage regulator that uses zener diode, and we have some assumptions. The assumption being the VI is variable, R and RL are fixed. This load resistance and this current limiting resistance are fixed. Okay, so you just find the expression for VI max. So Satish is not able to hear me. Satish, Are you not able to hear me? Is your problem still there or it has been fixed already? Satish Barik? Yes, Satish, are you able to hear? Anybody else is facing the problem of my voice not getting heard? Hello? Hello, others just respond to me. Okay, Astos has got no problem. Okay, that may be a local issue on at the Satish end. Okay, okay, Satish Barik, you must be having some network issue in your at your hand. Okay, okay, okay. No problem. Okay, others are having no problem. So you just keep trying. Okay, okay. Let us go to the simulation part. So let us get a zener diode from master database. Group I select is a diode. So which kind of diode do I require? I must select from here. So I require a zener diode. So I will select some zener diode. There is a list of zener diodes in the library. So let me select a popular diode. Okay, let me Google some zener diode. That is zener diode. Let's say silicon diode, zener diode, zener diode. This is it. Okay. So if I'll open a typical any, so this is some specification sheet of a zener diode. So what is its name? The zener diode has got its name 1N4740. So you can download the datasheet if you want to know more about this zener diode. Okay, it says 3.3 volt, 76 milliampere, 1 watt silicon zener diode. Okay, so this page at least lets me know that this is a diode which is a silicon based zener diode. Okay, so let me try to find out this diode in my experiment 1N4740. 1N4740. Yes, I have got this diode in my library. So I have got it on my virtual breadboard. So if you want to know more about this diode, zener diode, I can go to edit model. So here the specification is provided. Okay, the specification of this zener diode, this particular zener diode is given here. So this is the saturation current, this is reverse saturation current, the parasitic resistance, and lots of other parameters. The value of different parametric values, it has been given in this table. Okay. Can we find the zener breakdown voltage? This is the knee voltage, junction potential, Vj. Yes, this is the reverse breakdown knee voltage. Okay, so for our reference, I should better take note of it. The reverse breakdown voltage of this particular zener diode is 10.05 volt. Okay, whereas the forward knee voltage is 0.75 volt. So different specification values, okay, different the value of different uh, values, different parameters for this diode can be found from this table, or you can directly see from the specification sheet which can be downloaded from the website. Okay, so let us start using the diode. So I'm noting it down, 10.05 volt. This is the reverse breakdown voltage. I'll be using this value, so that's why I should note it down. 10.05 volt, the reverse breakdown voltage. 10.05 volt. Okay. So Vz is equals to 10.05 volt. This is the reverse breakdown voltage. So that means when you provide Vd is equal to minus 10.05 volt, okay, at that time the diode enters into the breakdown region, the region that is zener region. And what is the diode we are using? We should also write the name of the diode. The diode name is 4740, 1N4740. 1N4740A. So this is the diode which we are using. For this, we have got the Vz equals to this much. Okay. Vd was also given. Vd was 0.75 volt. The knee voltage, not Vd. This is Vt. Vt. The forward knee voltage. It is given 0.75 volt. We have already checked it in the specification sheet. Okay, model parameters. So I'll rotate it. So I need a current limiting resistance. Let me get a current limiting resistance here. Basic. I want a resistor. Okay, 1K. Let me have a 1K resistance. I want another resistance to act like our appliance, our load resistance. This resistance will act like our appliance or the load resistance. So here I will be observing the output. I must place a ground reference also. So I should get a ground reference. I will get it from sources, power sources, ground. So here I will connect it to the ground. So this point I am providing the ground reference. So my input will be given here. My output will be available here. So as I said, this is typically the output of a rectifier stage. So so this is mostly DC, but not the best form of DC that we can get. This is a DC which is mostly with ripples. Okay. So in this experiment purpose, I'm giving a DC supply only. to study voltage regulation. Otherwise, you should always keep in mind that this is not a purely DC signal that is given to a voltage regulator. This is not necessarily a pure DC signal. It may or may not be a pure DC signal. So this signal can have ripples, but we want to minimize those ripples by regulating using this voltage regulator. Okay, then we'll give some DC supply here. Power source, DC power source. Okay. I'm telling again and again, although I am giving a DC supply over here at the input, in practice it is not a DC supply. It is not a pure DC supply. This is a DC which may be fluctuating, or it may have some variabilities with respect to time. For experimental purpose, I have kept it a pure DC. Otherwise, it is not necessary. So. So in this scenario, I have let's say this is suppose I change the value of this RL to 500 ohm. Okay. My load resistance is 500 ohm. To make it more relevant, let me change the name to RL, because this is a load resistance. Okay, this is current limiting resistance. Let it be R1. Let it be named as R1 only. Now, just calculate for me what is the minimum VI. Although I have kept it 12, I may change this value to some other value. Now calculate for this particular voltage regulator what is the VI minimum that is required to turn this zener diode on. Calculate it. What is VI minimum? What is the VI minimum that is required to turn the zener diode on in this circuit? Do it. I will check in the chat box. Reply. Do the calculation. We have already derived the formula. We have derived the expression. How to find it? So using that expression, you just find out what is the minimum VI for this circuit to turn the zener diode on. Your current limiting resistance is 1 kilo ohm. The load resistance is 500 ohm. Okay, Ashish Patra, he says 4 volt. Others, they should verify it. You will enjoy the lab only if you do the things. Okay, simply listening is not going to do any favor for you. Okay, Ashish Patra, you are saying 4 volts. Let others to reply. Okay, I'm waiting for some other replies. Okay, you have the expression VI minimum is equals to Vz into R plus RL by RL. So you have, from our specification sheet, we have Vz equals to 10.05. R is 1 kilo ohm. RL is 500 ohm divided by RL. RL is 500 ohm. So 10.051500 divided by 500. How much it is? You just calculate. How much it is coming? VI minimum.
30.15.
Hmm?
30.15.
30.15. 30.15 volts. So this is the answer. So this is the minimum VI you must apply so that the zener diode gets on. So when VI is 12 volt, what do you expect at the output? How much voltage will come out? At the output, how much voltage will you get? Calculate. You have already calculated VI minimum to turn on the diode. So when if you set VI is equal to 12, how much V output do you expect across these two terminals at the output? Reply.
Sir, 4 volts.
4 volts. So let us check if it is coming 4 volts or not. Let us place a voltmeter, then we can know only. Okay. Multimeter connected here, connected to here. We'll choose DC voltage measurement mode. Simulate it. Double click. Yes, it is showing 4 volt. So we are applying a VI which is less than VI minimum. VI minimum we have calculated 30.05, right? 30.05 na? Yes or no? 30.15 volt. So 30.15 minimum VI is required to turn the zener diode on. Otherwise, the V output will be same as VL. VL is getting calculated to be 4 volt. So we are getting 4 volt. So what if this input signal is 30.15, the VI minimum value? We have calculated na? 30.15 is the minimum VI to turn this zener diode on. So suppose I give 30.15 volt. What is expected at the output? Yes, tell me. How much voltage is expected at the output in this case? If I set the VI to be VI minimum, that is 30.15.
10.05 volt.
10.05. Why 10.05? It is equal to the general breakdown voltage. Okay. So let us check. So I will run this simulation. Let us check. So instead of 10.05, it is 9.9 volt. So approximately. So it is approximately 10, almost 10. Okay. So it is good enough to take it as equals to the general breakdown voltage Vz. Okay. If you'll still increase the voltage, let's say I increase to 40 volts. We already know that VI minimum is 30.15. But if I increase the VI to as high as 40 volt, how much voltage is expected at the output? Yes, tell me.
At
Hmm.
13.3 volts.
13 Q. Justify your answer. Okay, let us simulate. It is 9.981 volt only. We have already discussed this thing. No? Whenever VL is greater than or equals to VZ, that means VI, this is same as VI is greater than VI minimum. Saying this is true is same as saying that VI is greater than VI minimum. And in that case, the zener diode is already on, and in that case V output is equals to VZ. V output is equals to VZ. When this is not true, when VL is less than VZ, at that time V output is equals to VL. You can recall or not? When VL is less than VZ, V output is equals to VL. When VL is greater than or equals to VZ, V output is equals to VZ. Here the zener diode is turned on. Here the zener diode is off. So since we have given here in this simulation Vi is equals to 40 volt, that means Vi is already greater than Vi minimum. That means it is same as saying VL is greater than VZ. When VL is greater than VZ or VI is greater than VI minimum, then already the zener diode is turned on. When the zener diode is turned on, the output, the voltage potential difference across these 2 points, the output has to be equals to the VZ, the breakdown voltage of the zener diode, and the VZ is 10.05 volt. That is the value of VZ for this zener diode. And when you simulate it, it is saying that it is 9.98. It is so close to the zener breakdown voltage only. So it is exactly matching. The concept is actually matching to what we have discussed here. V output is equals to VZ. So the output we are getting here is 9.98, which is almost equals to VZ. I can show you a very interesting thing here. The same discussion which we have done now about the relationship between the output and input, we can do it in the form of a graph, and that will be interesting. And it will be more helpful if somebody is not able to understand. Let me name this wire be named as V output. Net name, so that this label comes out at the wire, at the top of the wire. Okay, this is V out terminal. This is with respect to the ground. So simulate, if I'll go to simulate, analysis and simulation, I'm going to simulate. Under the simulate, I'm going to analyze in simulation, and I'm going to DC sweep, source Vi, output is V out. So I'm trying to plot V out as a function of Vi. So let me do it. Have I missed something? Okay, let me try again. Simulate, analyze and simulation. This is with output, the out. There is 0 to stop value. Let's say 40 volt. So in what range do I need to vary the VI? So let's say 0 to 40 volt increment of 0.5. Run. Yes, I got the plot like this. So what is this plot showing? In reference to the circuit we have drawn, you see this is VI axis. This is VI axis. And this is V output axis. This is V out axis. So I have calculated, we have calculated, you have also calculated that VI minimum is 30.15. So you see 30.15 value of VI, this is the critical point. The curve behaves in a certain way up till this VI minimum. Up till this 30.15, this is V out axis. Okay, this Y axis is your V out axis. So in response to Vi equals to 30.15, up till this, the curve is linearly increasing. Why? Because V output is directly proportional to Vi in that case. From Vi equals to 0 to 30 volt, V output is simply equals to VL, and VL is simply what? Vi into RL by R plus RL by voltage divider rule. Okay. Beyond this, beyond 30.15, VL is such that VL becomes greater than the Zener breakdown voltage. Okay. When Vi exceeds the Vi minimum, at that time, VL calculated is getting greater than Vz. So that is going to turn the Zener diode on. And once the Zener diode gets on, the output across these 2 points is same as the voltage which appears across this on diode, the Zener diode which is already on. And we know that once the Zener diode is on, the voltage across it is simply the reverse breakdown voltage, that is Vz. So beyond this point, beyond this critical point, that is beyond that value of Vi minimum equals to 30.15, इसके आगे देखोगे अगर तुम, you will see that V output becomes equals to the Vz, and Vz we already know that, we have noted it down, that 10.05. Vz we have noted it down that Vz is 10.05, and here also in this graph you see that beyond Vi minimum, V output becomes equals to this value, which is almost Vz, close to 10.05, and we have already measured in the multimeter, it is 9.98 volt, it is almost equals to Vz. So the entire thing is quite getting reflected in this plot. Are you getting? Hello? Any doubt? If you can question, I will try to answer. Hello, students. Hello. Okay, reply on in the chat box. Are you getting or not? What I tried to explain you in through the by using that graph. Did you get it or not? If any doubt, you can also write it in the chat box. I will answer it. Okay, 3 of you, yes sir. Others, what about others? Yeah, Ashish Patra has got a question. He says, is there an voltage where zener diode, zener stops working? Huh, I told you, no? Just to recall you, during the discussion, I told you that uh, the way we have calculated VI minimum, you can also calculate the VI maximum. VI maximum gets calculated on the basis of how much maximum current this zener diode can handle in the reverse direction, and you will get it in the specification sheet that it is given with some IZ max. Okay, and that will let you calculate the VI max that can be given at the input of the voltage regulator. If you exceed this VI max, or rather you say if you exceed this IZ max through this zener diode, because you should always keep in mind once the zener diode is on, there is some current in the reverse direction. Okay, and when you go on increasing this VI, this reverse current also gets on increasing. Okay, so if you increase this VI up to VI max or beyond it, it is resultantly letting the reverse current through the diode to exceed beyond that IZ max value. And if any current through this diode in the reverse direction exceeds that IZ max value, okay, the heat will be so much, the heat generated in due to this that high current will be so much, it will be sufficient to damage this zener diode permanently. It will lose its VI characteristics permanently, so that is no more available as a zener diode after that. So for a healthy operation of this voltage regulator, the VI must be limited below VI max, or you can say this, it should be ascertained that the current through this, the reverse current through this zener diode bit should be below that IZ max. Then only the zener diode or this the entire voltage regulator circuit will be operated in a desirable manner. Okay. Yes, yes. Beyond IZ max, the zener diode loses its VI characteristics. It is as good as getting damaged. Yes.